we will discuss about Gay Lussac Law. Gay Lussac Law says pressure is directly proportional to temperature for given amount of gas, that is number of mole is fixed, and for given volume of gas, that is volume is also fixed. So we can write P is proportional to T where temperature is in absolute scale. That is, we have temperature is measured in Kelvin. So we will have P is equals to K times T, where K is the proportionality constant and the value of K will depend upon number of mole and volume also. So we can have different value of K for different number of moles and different volume. So value of K, the constant, also depends upon number of mole N and volume V. So if I have constant K1, number of mole is N1 and volume is V1, we can have constant K2 for number of mole N2 and volume is V2. So you'll have different value of constant if I have different moles and different volume. So K is basically a function of number of mole and volume. So we can say constant K is a function of mole and volume. Let us plot a graph between pressure versus temperature. So we have P is equals to K times T. If I plot a graph pressure versus temperature, on the y-axis we have pressure, on the x-axis we have temperature. So this is by K is the slope m and temperature is on the x-axis, so this is x. Intercept here we have 0. So this is a straight line passing through origin. So if I plot, we will have this a straight line. Now in this region we have dotted line because at very low temperature gases gets liquefied. So there are no gases exist in this region and that's why we have dotted line. So basically in this case dotted line shows at very low temperature gases gets liquefied. Now let us plot pressure versus temperature graph, but now temperature is measured in centigrade. So this time temperature is measured in Kelvin scale. So this is temperature in Kelvin scale. Now if temperature is measured in centigrade scale, so this time let us say temperature is measured in degree centigrade scale. That is, let us say temperature we have, that is T, and measured in centigrade scale. So first we have to convert this temperature in absolute scale. So we will have temperature in absolute scale and this is equals to temperature in degree centigrade plus 273. Now we can plug this value here, so we will have pressure is equals to K times temperature in degree centigrade plus 273. So we will have pressure is equals to K times T plus 273 K. So this is on y-axis, this is the slope, this is x, and this is C. So once again you see this time we have intercept, so line will not cross through the origin. So this time line will not pass through origin. So let us say what we have this time. This is the x-axis and this is the y-axis. So it will have an intercept, and 273 into k is the intercept. So this is intercept on the y-axis. So we will have a positive intercept, and this is a straight line, and this line will cut when we have pressure is equals to 0. So pressure is equals to 0, we will have temperature plus 273. So from here we have temperature is equals to minus 273 degrees centigrade, because temperature is measured in centigrade. So this line will cut to the x-axis at minus 273. So temperature here we have in degree centigrade, and this will cut at minus 273 degrees centigrade. At this temperature we will have 0 volume, a 0 pressure. Basically y-axis we have pressure and x-axis we have temperature. Now let us say we plot the same graph but different volume. So P is equals to KT. We can plot this graph for different volume. So let us say we have said this is a straight line passing through origin. So in this region we have dotted line, then we have a solid line. Now let us say this is at volume V1, this side we have temperature, this side we have pressure. Now let us say we want to plot a graph for volume V2 that is greater than V1. So how we will plot? Let us consider a particular point of this graph. This has this amount of pressure and this amount of temperature. If I increase the volume, so initially I have a sample of this. This contains a gas, and now I am increasing the volume, keeping the temperature constant. So temperature is constant. In both cases temperature is constant. So keeping temperature constant, if I increase volume, what will happen? Pressure will decrease. So initially I am getting this pressure. If I increase volume, I will get lesser pressure. So this will be the new volume, that is V2. So this means now my new curve will pass through this point. So this is at V2. Similarly, if I have a V3 that is greater than V2, I will have a curve that is even lower than this curve. So in this direction volume is increasing. So we can say these curves are basically called isochores. So curve for constant volume. So these curves are called isochores. So curve that has same volume is called isochores. Now let us do one exercise related to the idea whatever we have said. The temperature of a certain gas is doubled if the initially gas is at 1 atmospheric pressure find the percentage increase in pressure. and this can be done using P is equals to K times T. So let us say we have situation number 1 and then we have situation number 2. So temperature of a certain gas is doubled. So initial temperature, let us say T naught, final temperature is 2 T naught. If the initially gas is at 1 atmospheric pressure, so this is T1 is T naught, this is T2 is 2 T naught, initial pressure P1 is 1 atmospheric pressure. We have to calculate what is the pressure we have at situation number 2. So we can apply P by T is equals to constant. This means P1 by T1 is constant and P2 by T2 is also constant, and these two constants must has to be equal. So P1 by T1 is equals to P2 by T2. So if I apply this, P1 is 1 and T1 we have initial temperature is T naught, P2 we have to calculate P2 divided by 2 T naught. So basically P2 is 2 atmospheric pressure. So we can calculate increase in pressure. This is equals to 2 minus 1, that is 1 atmospheric pressure. So we can calculate percentage increase. That is initial pressure is 1 atmospheric pressure, so 1 divided by 1 into 100. So there is a 100% increase in pressure. So this time we have 100% increase in pressure. Now next let us discuss a demonstration of Gay Lussac law. And what we have in demonstration, we have a can. This has closed air. It will have some pressure initially. Now we start heating. So this can is heated. So if we heat this can, so if I increase temperature, pressure will increase. So pressure will increase. Now let us say suddenly put this can into ice bath. So now this can is put into the ice bath. So we have ice bath here. So suddenly temperature inside the gas will decrease. So there will be a sudden decrease in temperature. If there is a sudden decrease in temperature, there will be a sudden decrease in pressure also, because pressure is directly proportional to temperature. So pressure will also decrease suddenly. So now if pressure decreases, outside air will try to push this one, so can will basically gets damaged. So can will change its shape. Initially it is something like this. Now to this one, can will have a irregular shape. So can becomes distorted. Can will be distorted. This is because air outside will try to rush this one, and this can will have different shape. Let us watch this video. Now here we have a can. This is an empty can, contains gases, and it is heated, and there is a ice bath that contains ice around 0 degree centigrade. So as this is heating, pressure inside this gas will increase because temperature is increasing. So temperature of this can is increasing and pressure of this can is also increasing. Now a time will come, it will have very high pressure, and suddenly if I put this can into this ice bath, temperature will decrease suddenly. So pressure will also decrease suddenly. So air from the outside will try to rush the air and can will blast. So let us see what happens. If I put this here, can gets blast.